Today's lesson is on the elements and the periodic table, which can be found in sections 4.1 and 4.2 in your textbook. Alright, so chemical symbols are shown on the periodic table, and every chemical has a unique chemical symbol. When scientists first started with chemical symbols, didn't realize how many chemicals there were going to be, and so they first started with just one-letter symbols. So carbon is one example, and so the symbol for carbon, if you look at the periodic table, is just a C. The symbol for sulfur would just be S, and you can find these on the periodic table as well. The symbol for nitrogen is an N, and it's important to note that all of these symbols are capital letters. The symbol for iodine is an I. Right? The symbol for potassium actually comes from the Latin root of the word, which is kalium. So the symbol for potassium is actually K. It's not P. P is actually phosphorus. And tungsten is another example where the symbol doesn't fit with what we call it, but it comes from the name wolfram, and so the symbol for tungsten is W. And so once more elements had been discovered, they started giving them two-letter symbols. And it's important to note that the symbol only has one capital letter in it, so the second letter in the symbol is always going to be lowercase. So for cobalt, that symbol is capital C with a lowercase o. For silicon, it's going to be a capital S with a lowercase I. For neon, we have a capital N with a lowercase e. Nickel is a capital N with a lowercase I. And so you can see the trend is that usually it's the first two letters of the element, but not always, because sometimes there's going to be a little bit of overlap. Sodium is another one that we use the Latin naming for. So the symbol for sodium is actually Na. Okay, and the symbol for iron, again, it comes from the name ferrum. So it's Fe. Okay? I'm not expecting you to know these symbols. You'll be given a periodic table with the names on it on every one of your tests. But I do expect you to know that capital C lowercase o is different than capital C capital O, for example. Capital C capital O would mean a carbon and an oxygen because we have two uppercase letters, whereas capital C lowercase o would be cobalt. So those are two different things. Okay, so back in 1872, a scientist called Dmitri Mendeleev wanted to find a way to organize the elements in some way that made sense, that could tell you a little bit about the element, and some way to sort of keep them organized because there were a lot of elements being discovered. So he actually says that the version of the periodic table that he eventually published came to him in a dream, and this is what it looked like. And so he organized them based on their molecular weight, so those are the numbers that are shown here. They go in order of increasing molecular weight, and then within a given row, for example, here we have chlorine, bromine, iodine, for example. In that given row, those elements share certain characteristics, and the same thing is true of, for example, oxygen, sulfur, selenium, tellurium. Okay, and that's true of all of these rows here, and then they're organized in orders from 9 to 12 to 14 to 16 to 19, 23, and then in the next row it continues to go up. Okay, and one of the other things that's really interesting about the periodic table that Mendeleev came up with is that it actually makes predictions about things that hadn't yet been discovered. So for example, right here in the periodic table and right here in the periodic table, you see question marks, and those are elements that we now know exist, and his predictions about their properties and their molecular weights and everything are actually very accurate. This is our current version of the periodic table, and you'll notice it looks very similar to the one Mendeleev presented, but it is rotated 90 degrees from the way he presented it. So first we're going to talk about the groups in the periodic table, and a group is essentially a column. Okay, and the columns, not all of them have names, but we're going to talk about the ones that do have names. So I'll just label them with colors, and I encourage you to color code yours in the same way at the front of your note packet. The alkali metals, I'm just going to color those this orangey color, and they are this first column here. Sorry, not hydrogen, but the rest of that column. Okay, so that's group 1A. 1A. Okay, the alkaline earth metals are group 2A. Label them in a blue color. Okay, and they are this group here. The middle section, those are called the transition metals. And that's this whole group here. Okay, and that is definitely more than one column. Okay, but it's because the ones in the middle there have different properties than the ones on the ends. This is the transition metals. The noble gases are the last column over here. Okay, and these tend to not be very reactive at all. Those are column 8A. And then the last one that we're going to talk about is the halogens, and they're in column 7A. And we'll make those yellow. And those are these here. Okay, and each of these groups has a given set of properties, and usually it has to do with their reactivity. And ones I'm going to talk about today are ones that students often find to be most interesting. These are the alkali metals, and I have a little video to show you.
Whether you've left school or you're still at school, you can appreciate the sheer fun and mayhem that chemistry can be. There's so much to it. Bunsen burners, mixing chemicals. Very nice. Now, you may have been allowed to mix very small amounts of lithium with water. You may, if with a responsible adult, have mixed H2O with sodium. And you may, under very strict scientific control, have witnessed potassium mixed with water. But the odds are, if you have, it will only ever have been on one of those rubbish science videos. There you go, make a present. These next two are the dog's nuts of the periodic table. They are, if you like, the king and queen of alkali metals. Mix these babies with water, stand well back, and watch the mayhem. And that's just what we're going to do. Mr. Tickle, bring on the rubidium.
Here it is.
Is that it?
Well, it might not look like much, Richard, but it's a highly reactive metal. It's sealed in this glass tube under argon atmosphere conditions, just for safety.
Right, so what's going to happen when you drop that in the water?
Well, imagine, if you will, letting off a hand grenade in a bathtub.
Righto, I'm off. Have that.
Okay.
Good luck. Okay, Tickle. Drop the rubidium in the water.
Stand back, everybody, this one's going to be bad!
2 grams of rubidium will only react when our specially designed vial dissolves in the water, which gives John a few crucial seconds to get into our safety zone. That is more like only on Brainiac do you get that kind of science. But I believe we can go one better. There is one more alkali metal we can legally use.
Yes, Richard, cesium, the emperor of alkali metals, particularly nasty, could go off at any time.
And that's it.
Oh, yes.
Brilliant. I like it already. Now, what's that going to do when it hits the water?
Imagine a depth charge in a bathtub.
Fair enough, mate. I'll leave it to it. Good luck.
Thank you.
Okay, John, go for it.
Warning, 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 extreme danger, clear the area.
As our cesium sinks in the water, the rapid generation of hydrogen gas should produce quite an explosion. And it does. Magnificent. And I think that concludes today's experiment. There is, I should say, one more, even more reactive metal, frankium, but for some reason they wouldn't let us have any of that. So, there you go, today's lesson.
Never mixed alkali metals with water.
That is an interesting video that shows how the alkali metals, which are the ones in group 1A, react when you mix them with water. And as you should have noticed, lithium has a very teeny little reaction, and as you go down the periodic table to cesium, you get much bigger reactions. So this one is very reactive, and this one is just a little reactive. If you go, for example, to the halogens, which are down here, you'll find that fluorine is the one that's really reactive, and as you move down, they get less reactive. We're going to talk about why that is. For right now, I just want you to know the names of the groups, and when things are in a group together, it usually means that they have similar reactivities. The last thing we're going to talk about today is metals and nonmetals and metalloids. They're divided on the periodic table in this section here by a little zigzaggy line. And this zigzaggy line appears on the periodic table that we have up in the classroom, but is not on the periodic table that is given to you in your notes. So you probably want to label that line as well. Things that are over on the left-hand side of the periodic table are metals. Your book labels them in blue, so I'm going to do the same just to make it a little clearer. So the things over here, so that's the alkali metals and the alkaline earth metals, as you would expect from their names, are metals. And the transition metals, which we talked about, those are also metals. All right. Put them all in. Okay. And then over on this portion of the periodic table, aluminum is a metal, which I think most of you should know from working with things like aluminum foil. And then all of the metals not touching, or all of the elements not touching the jaggedy line are also metals. Okay, and so metals have properties that you would expect from your experience with things like copper and aluminum and nickel and silver and gold and things like that. They tend to be shiny. They are good conductors of heat or electricity, and you can make them into wires. They're ductile, that's their ability to be made into wires, and they are malleable, which is their ability to be made into sheets. Those are the metals. The nonmetals, we're going to make yellow, because that's what color your book makes them. And those are the things on this side of the jagged line that are not touching the line. And as you'll figure out as the year progresses, hydrogen is often a little bit weird, and hydrogen is also a nonmetal. Nonmetals tend to be less dense than metals. They're not shiny or ductile or any of those things. And where metals tend to be solids pretty much all the time, nonmetals can be any of the three states. All right, so the last group that we're going to talk about are the metalloids. And metalloids, which I'm going to label in green, tend to have properties that are similar to both metals and nonmetals. They're not as good at conducting as metals are, for example, but they're much better than nonmetals are. And so these are all the ones that are touching that jagged line that we drew earlier. So that sums up our discussion of the periodic table and the elements, and we will continue learning more about the elements in class.